Hello and welcome. In this video we will talk about how we can formulate a LQ optimal control problem into a standard QP problem, but very efficiently. In the last lecture we learned about LQ optimal control problems, and there we took into account a set point tracking problem formulation. Now let me rewrite the question for the LQ optimal control problem, just for simplicity. So this is the structure of an LQ optimal control problem, and this we discussed in a detail in the previous lecture. This LQ optimal control problem is not in a standard form, and that's why this has to be changed into standard QP problem or standard quadratic programming problem. The core concept in this video is that we'll be using the Kronecker product formulation to convert an LQ optimal control problem into a standard QP problem, so that we can use the solvers to solve this standard QP problem in Simulink. I would like to denote the number of states as nx. And also an LQ optimal control problem is formulated using the discrete-time model of the process, which is a linear discrete-time model. Alright, now let us use the Kronecker product to convert into the standard form. The standard QP problem has z as the number of variables to be optimized, or in this standard form, we have used the variable z to denote the decision variables. So the first step in converting the LQ problem into standard form is to define this unknown vector, or the decision variables, which is this z variable. The z variable can be defined not only for the control inputs, but also for other variables such as the states, the outputs, and the error signals. Well, with the control point of view, we know that one of the unknowns that the optimizer should optimize is the control input. So that has to be included in the z vector, but in addition we could also have states as unknowns to be optimized, and the error between the set points and the process output, Remember that z is column vector, so it has multiple rows but only one single column. Then if you take the transpose of z, then the z transpose will become something like this. And of course, for multiple inputs and multiple output or MIMO systems, you can be able to control not only just one control inputs, but many control inputs. So you could in itself be a vector. Similarly, there can be more than one state in a process, so this x in itself can be or vector more than one states. We could also control not only just one single output at a time, but more than one outputs we can control simultaneously. Therefore the error between the set points and the output variables to be controlled, which is this e, can also be more than one. So this e can also be a vector, and similarly there can be more than one outputs in a process. That's why this y can easily also be a vector. So for a MIMO system with multiple states, all of them in itself are vectors. And if we represent nx to be the number of states, and ny to be the number of outputs, and nu to be the number of control inputs, then we can also find the size of z. But before we can find the size of z, we also need to understand that this LQ optimal control problem is defined for the whole prediction horizon. And n here means the prediction horizon, which means that the vector of unknowns, which is the z, contents the unknown values of u not only at the current time state, but throughout the horizon. And similarly the same idea or the same also applies for the states, the error, and also for the outputs. Or in other words, all of these unknowns which are defined in this vector z are not only for a single time step, but for the whole prediction horizon defined by the capital letter N. That's why if you want to find the size of z, you have to include the size that would arise when we take the whole prediction horizon into account. Let us do that. Here we have u, and let's consider that it's a MIMO system, and it has in u number of inputs. Similarly, we have also x, or here in fact, so the unknowns gets added, x is also an unknown together with u. And similarly e is also unknown together with y, and since e is the error between the reference and the control outputs, the size of e should be the same as the size of y, or in other words y defines e, so for e we will have in y, and finally for the outputs we have in y number of outputs, considering it as a MIMO system. So this number of unknowns would be there, but since we have to consider the whole Horizon we have to multiply with capital N, or the length of the prediction horizon. Now let us expand this LQ optimal control problem's objective function. Let's open up the summation sign and write a long line of equation. The thing that we are doing here is that we are putting the values of k from 1 to n into this function. So for k equals to 1 it will be E1 transpose Q1 E1 for k. Equals to 2 it will be E2 transpose Q of 2 E2. And similarly the same thing also applies for the control input. Now for the control inputs we can also expand it. Here this starts with 0 not with 1 as in the error signal, because here we have the index k minus 1. So if you put k equals to 1 then 1 minus 1 is 0 and so on. And if you put k equals to n the last index then it will be n minus 1. Let us also expand the objective function of the standard QP problem formulation, or in other words let us also expand this function. Since our z vector contains the following elements, let us write them. This is our z vector, or in fact z transpose vector, so we can also transpose it here. For the h vector we can split the h vector into the following structure. Here we have taken from h11 up to h44 on the diagonal, because we have 4 different types of unknown variables to be optimized. This is h, then we will also have z, and we know z is simply this one. Now we also have the linear term. Now let's also expand this one, so this is z, similarly this is also z, and this is c transpose, and here we have taken c transpose as c1 to c4, because we have 4 different types of variables included in the z vector, so it becomes easier for also include from c1 to c4. Alright, so this is simply a plain expansion of the compact form. Now let's open or do matrix calculations here. If we multiply this vector z transpose h of z, then what we get is that u transpose gets multiplied with h11 and gets multiplied with u, so then we will have u transpose h11 and u. Since the other elements are 0, u transpose multiplied with 0, and then with x will become 0. So we don't have to write it, and similarly u transpose multiplied with this element, and with e becomes 0. Similarly for y it becomes 0, so we don't have any combinations of u with x. U with e and similarly u with e, u with y, so all of them are 0 because we have 0 on the upper triangular matrix. The same concept also follows for the zeros on the lower triangular matrix. Then we will have to multiply the second element, which is the x, and now it's very clear or easy to understand that x will be multiplied with only x because h22 is on the diagonal rest of the multiplication becomes 0. Then we will have. Let us consider that this is equation number 2. Now if you compare equation 1 and equation 2, we see that they both are the objective functions. And if we compare them we get the following thing. For example, here we have the e terms, and since they are the same objective, then the whole e term should be equal to this term in this equation number 2. Okay, then we can write it. Now we can write this algebraic equation into a compact form using matrices. Let us do that. So the right-hand side of this equation has been written in the compact form. And now if we compare the left-hand side to the right-hand side, they are the same, of course. So now we can say that of course E transpose is this 1. E vector is all of the errors from index number 1 to the whole prediction horizon n. That's why H33 must be this one. And in most of the cases, the weighting matrices Q1, Q2, and NQN are considered to be the same throughout the prediction horizon. That is. And this matrix can be written using the Kronecker product. Because this is a very well-structured matrix, the Q's are on the diagonals, these are all Q's and all of them are zeros, so this we have already discussed previously, and this structure is similar to writing as the following. Or the Kronecker product between Q, which is the weighting matrix, and an identity matrix of size equals to the prediction horizon. If you take the Kronecker product between these two you will get exactly this matrix. So this is a compact form. Similarly, if we keep on comparing equation 2, which is this one, with equation 1, which is this one, then we can see that you transpose H11 from equation 2 must be equal to all of this one. That's why we can write Just like before, we can now put this right-hand side term into matrix form. This is U transpose, and this is H11, and this of course are U vector. So if you multiply U transpose H11 and U will get this function back again. So comparing both left-hand side and right-hand side, they are the same. That's why finally we have H11 matrix as follows. Normally P, which is the weighting matrices for the control inputs, they are also taken to be same throughout the prediction horizon. So from k equals to 0 to k equals to n-1, this P can be kept the same or constant. And this matrix where the weighting matrices are only on the diagonals and all of the other elements are 0, also has a very special structure, and this can be written like this with the help of Kronecker product as follows. Here IN is an identity matrix of size equals to the prediction horizon, and P is the weighting matrix, and the weighting matrix P is a diagonal matrix with the diagonal elements being equal to the number of control inputs. And if you multiply these two matrices, you will obtain this matrix. Let's keep on comparing, and if you go back to equations 1 and 2, here we can say that in equation 1 there is only E term, and U term, no other terms are here in equation 1. In equation 2 we have already seen the U term and the E term, the remaining terms which are the X and the Y's, which are only in equation 2 and not in equation 1, should be 0. When we compare these two, so X term and Y term should be 0. Or in other words, we can also write this as follows. The first element, which is x1 of the x vector, gets multiplied with 0, and with x1, which means that the whole term is 0. Similarly, for k equals to 2 index, we multiply with 0 all the way throughout the prediction horizon, where k becomes equals to n, and this equation can be written in compact form like this one. If we compared the left-hand side to the right-hand side, we can see that H22 is equal to this middle matrix. And this matrix, which contains all elements to be 0, can also be expressed effectively using Kronecker symbols as follows. Here 0 means a matrix with all elements zeros containing nx number of rows and nx number of columns. So if we take the Kronecker product with an identity matrix, we will get this matrix. Or in easy terms, we can also write like this. This is a matrix of zeros which has n dot of nx number of rows and n dot of nx number of columns. Here we have to take into account n dot of nx, and not just nx. Because x are from k equals to 1 index to k equals to n, or all the prediction horizon, is taken into account. Soon dot of ne. And at each index we have nx number of states. Here also nx number of states. And so on. That's why in total we have n dot of nx number of elements. We have already done for H33. And finally we can go and compare the y term, which contains H44. And this y term is not there in equation 1. Here it's only E and U. So that becomes also zeros. Comparing both sides, we know that H44 is this matrix containing only the 0 terms. And we can express this 0 matrix using the Kronecker product as follows. In MATLAB or in MATLAB function block and Simulink, we can write these zeros as. Now we have found out the matrices for H11, H22, H33 and H44, which are needed in this standard QP form. We still also need to find out the values for this C transpose vector, or in fact the C vector. In the LQ optimum control problem formulation, or set point tracking problem, it only has quadratic terms. There is no linear terms. That means the linear term of the standard quadratic optimization problem should be 0. When we compare this one, or when we change this one into this one. Here there are no linear terms. So C transpose, or C, is simply a vector of zeros. C should be a vector of zeros. But how many zeros should be present in this C vector? It's very easy to see that. Look here. The C vector is being multiplied with Z. See here. The C transpose vector is being multiplied with Z, which means that the C vector should have the same number of rows as the Z vector. And what is the size of the Z vector? The size of the Z vector is n of Z. That's why the C vector will also have the same number or same size, which is nz number of rows and single column. Now we have finished. Okay, thank you. We have finished defining the H matrix and the C vector in the standard formulation. We have done this part, and we are also done with this part. Now we have to formulate or find out the matrices AE, BE, AI, BI, and so on by using, or by converting this equality constraints into this standard form, and this will be done in the next video. Now let me summarize. After comparison, we have found H11, we have found H22, and similarly the C vector is also found, and the C vector is. The H matrix is the diagonal matrix or a block diagonal matrix where the diagonal elements are H11 matrix, H22 matrix, all the way to H44 matrix. Thus we can write with this command book diag. We'll make a block diagonal matrix with the following elements on the diagonal. If you enjoyed this walkthrough of actual video, hit that like button and subscribe for more hands-on MPC content. Thanks for watching, and see you in the next video.